In this video, we're going to talk about chirality. We're going to talk about the definition of chirality, what it means, and talk about how these are part of optical isomerism and stereoisomerism. We're going to get you to identify chiral centers and also get you to go through how to draw different optical isomers. So stereoisomerism is the area of isomers where this chirality, this optical isomers, exists. So if I go through the isomers to begin, there is your isomers and there is your normal isomers, which you do in the first part of the course, which is structural isomers. And again, try and think of this definition, because you might get asked this definition in the exam. And it is same molecular formula, different structural formula. Now, when you're doing structural isomers, you generally put them into three different types, and those three different types allow you to draw all the necessary isomers. And in a rare occasion, sometimes they ask you to draw only one type. So the first type is positional, when you just change your functional group position on the chain. And then you get your functional group one, which is where you change the functional group. For example, aldehydes and ketones are functional group isomers, and cycloalkanes and alkenes are functional group isomers. You can then do chain, which is when you just introduce branching and such and so forth. But we're not going to do that side. We're going to do the stereoisomers side. So you can have structural isomers or you can have stereoisomers. Now, the definition of stereoisomers is the fact that it is the same structural formula but a different arrangement of atoms in space. But we'll show you that on the next slide. Now, stereoisomers splits into two different sections. So it's the EZ isomers and the cis-trans, and that's when you do it with alkenes. And then the optical isomers, which we're going to do today. So we get rid of what we don't need and move the rest up. And there you go. And we're going to focus on our optical isomers. But before we do that, let's remind you of what the definition was for stereoisomers. So molecules that have the same structural formula, but different arrangement of atoms in space. It's so often asked, so make sure you know it. Now, we're going to focus on the optical isomers. So those optical isomers can also be called enantiomers. And enantiomers have a definition. So if you're ever going to define optical isomerism, if there's a question that says define optical isomerism, you have to say non-superimposable mirror images, also referred to as enantiomers, and they are optical isomers. Okay, so definition of optical isomerism, non-superimposable mirror images. We're going to go on now to explain what that actually means. So there's optical isomers, okay, these enantiomers. Now, chirality stands for handedness. So what I'm going to do now is we're going to go to the lab and I'm going to show you what this looks like using molymods and using our hands. So welcome to the lab so I can explain the wonderful world of chirality. Really interesting subject where a tiny little change in a molecule can give you a different taste, a different smell, or a different effect, for example, in terms of drugs. Now, the word chirality is Latin for handedness, so we can explain it using our hands. So if you put your hands in front of you and then you put them opposite each other, you can see they're mirror images of one another. You can also see that if you superimpose them on top of each other, they're non-superimposable because your thumbs stick out. Now, another thing to notice is that your hands are made of the same parts in the same essential order. So you've got 4 fingers and 1 thumb. Now, if we go back to our definitions, a stereoisomer is the same structural formula, so same atoms and same order that they're in, okay, and a different arrangement of atoms in space. So in this case, the thumbs are arranged in differently in space. So the optical isomers are when you have the non-superimposable mirror images, which our hands are. Okay, now let's go from the hands, because that's why we name it chirality, and look at the different optical isomers that you create because of this chirality. So we have 2 molecules right here, and the 2 molecules, you can see they're exactly the same thing. All the 4 colours line up and around this central black carbon. So to get these optical isomers, you have to have these 4 different groups around the central carbon atom, and they're represented by the 4 different colours. All you have to do, if you want to change this into a different optical isomer, so we have these non-superimposable mirror images, is take 2 of the groups and just swap them around. Now that means that the groups have a different arrangement of their atoms in space, essentially, and you can get these optical isomers. So if you look at this now, you can see non-superimposable mirror images. And these non-superimposable mirror images means they're optical isomers, which means they can have different tastes to each other, different smells to each other, and possibly different effects, for example, if they're used as a drug. So we're now going to go back to the studio where we can explain all of this in terms of an exam-style questions and scenarios and get you to draw these different optical isomers. So you've now seen in the lab that you can have models, and that shows this non-superimposable mirror image with your hands and with these models. So the definition is of a chiral carbon that you have a chiral center, and that chiral center or chiral carbon has 4 different groups attached to it. So you need a carbon with 4 different groups, as we went over in the lab. The most common example of that is an alpha amino acid, which is the one you'll use most predominantly in the questions. And there's a great picture here that shows it. So we've got the 2 hands here, and you can see they're non-superimposable mirror images. Okay, and you can also see we've got an amino acid here. So what I would recommend when you're doing the drawings is you shorten your carboxylic acid to COOH, NH2, and then your H and your R. And you can see that these are mirror images of one another. If you put a mirror down there, you can see the R's line up, the COOH lines up, and the NH2s line up. Now, the chiral carbon is this carbon here. So you can see this carbon with 1, 2, 3, and 4 different groups attached to it. Unless you have those 4 different groups attached, you don't have a chiral center, a chiral carbon. So now let's go on to what that actually looks in terms of the drawing. And it's really important that you follow certain rules. And the certain rules are to draw those enantiomers. The easiest way of drawing the enantiomers, drawing the optical isomers, is to swap the 2 of the groups around. So just 2 of the groups, doesn't matter which ones they are, but I prefer the dash in the wedge just to make it really clear. Swap those 2 groups around. Examiners like it when you do things in a really simple way. And the simple way is swapping them around. And then they can quickly go, oh, that's definitely right, tick. Okay? So before we do that, we're going to draw our 2 optical isomers, our enantiomers, and if they're all at 50-50, they will be referred to as a racemic mixture. And lots of optical isomers come in these racemic mixtures. So let's look at our amino acids. So we've got a very simple amino acid here, okay, where your R group is CH3. And we're just going to draw the 2 enantiomers here. So let's, first of all, and this is the process every single time, you take your carbon, so your carbon that is at the center, and you draw 2 bonds in the plane. So there's your 2 bonds in the plane. You then draw your dash and your wedge. And you just get used to drawing that picture. And then it doesn't matter how you put your different groups on, because we know our chiral carbon is this one here. Okay, so there's our chiral carbon. So we just take the groups off. I like to put my H pointing up all the time. I do it the same every single time. And then I just put anything else anywhere else. So I'm going to put my CH3 here. Okay, I'm going to put my NH2 here and my COOH here. So I've drawn, that's my 1 enantiomer. Now, the easiest way to draw the mirror image, you can just draw the mirror image, you can draw a mirror here and then draw out the mirror image, is to take this one and then draw exactly the same thing again. So I'm going to draw my H and I'm going to draw my CH3. They're exactly the same. And then as I've said down here, swap 2 of the groups around. Okay, so I'm going to take this NH2 here, I'm going to take the COOH, I'm just going to swap them around. So there's my dash, and here is my wedge, and I'm going to put the NH2 down here, and I'm going to put my COOH there. So what I've done is, without actually doing the mirror image, because I can just do the mirror image, I've created two mirror images just by swapping those two groups around. You can see NH2, COH, and then COH, NH2. Simplest, easiest way of doing it. If you're a visual person, you can do it like a mirror image if you would like. But I find the easiest way is to do it with swapping the two groups round. And if you just practice this, change your R group up here, okay, change it, you choose different amino acids, lots of them are chiral because they have 4 different groups attached to that carbon, okay, and you can practice drawing these and you'll get very good at them very quickly. We're now going to move on to the final part of this video. We're going to talk about different labels for different optical isomers and enantiomers. And this is really one of the most interesting parts, and I love teaching optical isomerism, and I love doing it practically. That's because these are the brilliant molecules that can basically are just mirror images of one another. You couldn't really tell the difference unless you lined them up, and yet your body, your nose, the biochemistry within your body can tell the difference between these molecules, and sometimes they'll smell different, sometimes they'll have different effects on your body, okay, and in terms of drugs, and that also means that your body is such a wonderful thing that just has these receptors that are just so good at just telling the difference to what is essentially just the same thing but a mirror image. It's an amazing thing. So here we have the enantiomers and the terms we give them. So we give them a right and a left. And I'll explain why that right and the left is. The right converted into Latin is rectus, and then sinister for the left, and then they shorten that to R and S, and that's how you get to the R and S. So what is the right and the left actually for? So we've got carvone here, and carvone here is the R enantiomer, the R optical isomer. And we can see if I go across here, we can see that our chiral center is right there. You've got 4 different groups. And remember, if we're looking for a chiral center, we're looking for 4 different groups. There's a different group, there's a different group. And then if we look up and look to the left, that side is different to that side. So we've got 4 different groups attached to here. And we'll go over an example of identifying these chiral carbons when we do the exam style questions video, which is next in this series. Now, if you look at here, this chiral center can be identified. And like I said, identified at R. So we're going to draw the other enantiomer in a second over here, but first of all, why is it that R? So it's that R because of this machine. And now this is a very small machine, about this big, but when you split it out into this wonderful graphic, okay, this graphic shows you that the light is a plane, so it's just literally like that, up and down. You can see it's up and down. You see the direction here on the arrow. And you can see that as it's going through the liquid is in this grey container right here. As it goes through the liquid, you can see it's starting to turn. And you see it's starting to turn that way. So starting to turn this way. And this one is turning to the left. You can see it's turning there to the left. And then the person looking the other side can see that it's turned to the left. Well, that means the optical isomer inside here, the enantiomer in here, is going to be left, the S. And it's this rotating the plane of polarized light which allows you to tell what enantiomer you have. So the R rotates the plane of polarized light clockwise. Clockwise is to the right. Okay, and S rotates the plane of polarized light anti-clockwise, so to the left. Now, that means you can have 2 different enantiomers, and those 2 different enantiomers can be given labels as we have done in carvone here. And the really clever thing, if you've ever done it, the R enantiomer smells of spearmint, which is a very nice smell with carvone, and then the S enantiomer smells of caraway seeds and can even have a slightly different taste as well. Again, how amazing is our body? So this is really important though for when you're drawing enantiomers. You won't necessarily be assessed on all of this information in terms of the R, labelling the R and the S enantiomers, but it's useful to know for answering those really high level questions, which we'll go over in the exam style video. Now's your chance to try the different type of chirality questions in the exam style questions video which is next in the series. Please try and attempt them as you go along, and you'll find very quickly you'll become very good at drawing chiral molecules.